Hello, my name is Tyler Franzak. I'm a graduate student in Full Sail's Mobile Gaming Master's Program. If you'd like to learn more about me or my work, feel free to check out my website. Otherwise, without further delay, I'll move on to the main purpose of this recording, which is to demo the functionality of my capstone project, Game AI Simulator. Game AI Simulator is a simulation application for Android that is targeted at employers within the video game industry. This app enables experimentation with the distilled fundamentals of modern game AI. The entire premise for this application is the exploration of game AI concepts in a manner that can be described as comprehensive, interactive, and informative. As this is not a traditional game experience, but rather segmented interactive demonstrations, there is no narrative to consider. Currently, the project's major systems include a runtime level editor with dynamic mesh creation, agent navigation with optimized A-star pathfinding, post-processing, and steering behaviors, influence mapping, finally, a behavior tree AI architecture. Now you have a vague idea of the project. I'll go ahead and start up the app on my NVIDIA Shield Tablet K1. It's important to note this application is fully supported in smaller devices as well, such as an LG phone. Upon starting the app, we find ourselves in the main menu, which has the options of select mode, credits, and exit. Choosing select mode reveals 3 available modes. I'll start off by demonstrating the pathfinding mode. In the pathfinding mode, one of the first things you will notice is a panel of options on the left side of the screen. This panel is comprised of toggles and drop-downs that modify the pathfinding. More options can be revealed by using the panel scroll bar. Finally, this panel can be disabled and then re-enabled by pressing the button in the lower left. To the right of the panel is the terrain that is constructed at runtime using the custom level editor. Every terrain mesh is constructed from saved binary files containing only elevation and texture data for each cell. In the center of this terrain is an agent, which can be seen more easily by adjusting the zoom level using the standard 2-finger input. The camera can also be moved by dragging one finger across the screen. Once satisfied with the camera's zoom-in position, a target destination can be chosen for the pathfinding agent by pressing a cell in the terrain. Its default pathfinding is achieved using A-star that has been optimized with a min-heap priority queue. To display the nodes that are explored during each search, the toggle Show Search can be selected. A cell with a white outline indicates that its corresponding search graph node was not considered during the search. A green outline indicates a node that was added to the priority queue but was not explored, while a red outline indicates a node that was explored and marked as being in the closed list. Therefore, an efficient search is generally the one with the lowest number of red outlines. If you are familiar with A-star pathfinding, you've likely realized that the search pattern is not indicative of A-star. This is because the heuristic is set to none, which can be corrected by selecting admissible or overestimated. Further search optimization can be seen by pressing the hierarchical pathfinding toggle. Hierarchical pathfinding is achieved by first performing an A-star search across the region graph, which is dynamically constructed based upon cell elevation. This graph can be seen by pressing the Show Regions toggle. After calculating region path between the agent's current location and destination, the subsequent cell search can ignore any nodes that are not within the region path. The final search modifier is the toggle Penalize Deviations. What this does is add an additional cost to any nodes that would cause the agent to change its direction. While this can slightly reduce performance, it produces paths that are more natural with a reduced number of turns. Once a path has been created, it can be smoothed using the Smooth Turns toggle. This is done by calculating a Kaplan-Rom spline between each original path point. While this does result in a smoother path, it creates an excessive number of new points that have to be stored in memory and tracked by the agent. To counteract this, the prune points toggle can be selected. What this does is iterate over each point in the path and check its collinearity with the 2 previous points. Should these 3 points form a line, the middle point in that set is then removed. The final thing to mention in the pathfinding mode is the menu button in the screen's top right. This reveals options for restarting the current mode or for returning to the main menu. I'll quickly demonstrate the restart button, which will reset the camera panel as an agent. Next, I'll select the main menu button, navigate to the select mode, and open the steering behaviors mode. In steering mode, there's once again a control panel with various options, this time utilizing slider UI elements. As far as loaded terrain, the cells are at different elevations, and there are 2 different textures being used. The biggest difference is the existence of numerous agents navigating along the terrain. Each agent, if I zoom in a little bit closer, has blue and red lines of various lengths protruding from the center to indicate their current velocity and their steering vector. The current steering behaviors being demonstrated are seek and separation. The seek behavior causes each agent to steer towards a target destination, which in this case is denoted by a green cube. If the user so chooses, as I will right now, they can move the green cube by tapping on a cell. Second steering behavior, separation, causes each agent to steer away from the other agents should they become too close. To change the current steering behaviors of the agent, a new selection can be made with the drop-down. After selecting Pursuit and Wander, a blue circle appears in front of all the agents, with the exception of one. If you zoom in very closely, you can see a green circle within each blue circle. The green circle represents the agent's target destination relative to its current position, which is randomly adjusted by a small random increment after each movement. The green circle is restricted to within the bounds of the blue circle. This results in the seemingly random movement pattern known as the wander steering behavior. It is important to note that there is also an unmentioned steering behavior at play, which is collision avoidance. This behavior causes the agent to steer away from an imminent wall collision. As far as the pursuit behavior, this is only active in the orange agent, which attempts to intercept a random agent at a future location. After a short period of time, the orange agent randomly selects a new target. Next, I'll select the leader following behavior, which is actually a combination of many smaller behaviors. The leader, represented in orange, attempts to steer towards a target destination marked with the green cube. The leader's behavior is similar to the seek behavior, but is actually known as arrival, because when the leader is in close proximity of the target, he will slow down so as to not overshoot the target. The other agents are using the separation, collision avoidance, and seek behaviors. They are seeking a target destination that is always positioned behind the leader. This all comes together to create the appearance of a group being led to a target destination. Finally, I'll go ahead and demonstrate the last behavior, path following. As soon as this behavior begins, 3 small cubes appear in front of each agent. The red cube indicates a future position based upon the current velocity of an agent. The black cube represents that future position projected upon the current line segment. The green cube represents an offset position along that line segment from the black projected position. When the red cube falls outside of the path radius, the agent makes an incremental steering adjustment towards the green cube. It is important to note that the maximum allowable steering force must be strong enough relative to the agent's speed. Otherwise, the agents will be unable to correct their steering before they veer off the path. For example, if I crank up the speed, the agents will be completely unable to stay on the path. But if I increase the maximum steering force, they will have no problem staying on the path. Now that you've seen everything in the steering mode, I'll return to the main menu and select the ecosystem mode. On the terrain of the ecosystem mode, there are agents whose current behaviors are being regulated by a behavior tree architecture. An agent can be selected by simply tapping on their nearby tile, which reveals their field of vision. Information on that selected agent can be seen by pressing the button with the head icon in the bottom left, which reveals that selected agent's ID, age, hunger, weight, and BMI. Behind the scenes, the energy expenditure of each agent is being calculated based upon its metabolic rate, current activity, weight, and simulation time step. That energy amount in kilocalories is then added to the hunger value of the agent. If the hunger value exceeds the agent's metabolic rate, the agent begins to starve. So the energy deficit is deducted directly from the agent's weight. Starvation also has behavioral effects on the agent, causing them to become violent, indicated by the color change to red. If one agent kills another agent, it can then eat the meat that is left behind, thereby becoming placated. In order to see those behaviors, make this mode a little more interesting, I'll switch back to the control panel. By pressing the addition or subtraction buttons, the number of agents, the current agents, can be modified. Additionally, there's a slider that can be used to adjust the spawn rate of the plants. The final option in this mode is the ability to toggle the population map. This influence map is a visual representation of agent density. Each agent acts as a source of influence, which is registered by the region the agent is within. This influence is then propagated to other regions with a linear fall-off algorithm based upon region path distance, momentum, and decay. Constantly calculating path distances between each region will be computationally taxing, so the propagation calculations utilize pre-computed distances stored in a dictionary. In general, the greater distance between a region and an influence source, the less that region's influence value will be affected. However, the degree to which this is true is based upon the values of momentum and decay, which can be seen by scrolling down with the scroll bar. Momentum regulates the rate at which an agent, or rather a region, will be affected by influence. For example, if I use the slider to lower the momentum value, each region's influence value changes at a slower rate. Whereas if I raise the momentum value, the region influence values will change almost immediately. Decay regulates how far influence will spread. For example, if I use the slider to lower the decay value, the entire map will flood with influence. Whereas if I raise the decay value, influence will barely spread out from each agent's region. Now you've seen all the project has to offer, I'll go ahead and return to the main menu and briefly mention two specific things that this project is sorely lacking. The first deficit is the absence of any type of codex or encyclopedia to provide essential context to individuals that are not familiar with game AI. The other deficit is regarding the number of AI behaviors available in the ecosystem mode. There's some sense of life created by the existing behaviors, but there are many essential behaviors missing, such as sleep, fighting, fleeing, and mating. Despite the project not being in an ideal state, it did accomplish its primary objective, which was to demonstrate a fundamental understanding of game AI. Going forward, this project will allow for further exploration of more advanced AI concepts. That is going to wrap up the screencast. I hope I was able to give you a good impression of the work that was done on Game AI Simulator. Thank you for listening, and take care.